Hello and welcome. In this video, we're going to talk about complex numbers, also referred to as imaginary numbers, that involve I, and where that idea came from and why it's important. So let's go ahead and jump right in. So we have been talking about solving quadratics using a variety of different methods, but we have gotten to a place where we said a quadratic can either have one solution, meaning our quadratic crosses or touches the x-axis once. It could have two solutions, meaning it goes through the x-axis twice. Or we've said that if it never crosses the x-axis, it has no real solution. So the idea is these quadratics that we're thinking about graphically to talk about our solutions are really just functions that can be written as such. So for example, we could look at the function y equals x squared plus 4. If I graphed this function, it would not cross the x-axis at all, which we would say means it has no real solutions when we're thinking about solutions as where it crosses the x-axis. But if we think about this, if we just take the graph away for a minute, if we just look at this as a function, and what we're really saying is, I want to know when does this function equal 0, we can mathematically look at this and say, well, this would be the same thing as x squared equals -4. And how do we solve this? We take the square root of both sides. And we learned a long time ago that we can't really, in the real number system, take the square root of a negative number. So we would say, again, that this is no real solution. Well, functions that behave in such a way as this quadratic here, there still are numbers that we could think through that would help us solve this type of problem, and that's where the imaginary unit came in. If this negative sign wasn't here, you would tell me that the square root of 4 is plus or minus 2, which means we could actually solve this quadratic. But how do we accommodate for the fact that this was a negative value? The way for us to say these are our solutions, but they're not 2 and -2 on the x-axis because this graph doesn't cross the x-axis. They're 2 and -2 on this imaginary axis that has this negative. And that's where the idea of I came in. So I is really just the square root of -1. So if I had something like the square root of -3, I could rewrite that as I times the square root of 3. So it's sort of like a placeholder to tell us that the solution here isn't crossing the x-axis, but it is something that we could still solve, and that's where imaginary solutions come in. This idea of imaginary solutions is sort of a weird thing, and the first thing that I thought when I was learning about imaginary numbers is, why did someone create something complicated to make me just have to do more work? But in reality, imaginary numbers, complex numbers, show up in a lot of different aspects of our lives, and I think the most specific application that you may see if you go on to take higher level physics classes is that imaginary numbers come into play when we're talking about electricity and when we're talking about circuits and how a circuit behaves. So there are more applications of them outside of just being able to solve a quadratic that doesn't cross the x-axis. But for purposes of this lesson, our focus is how do we deal with and manipulate when we have imaginary numbers? How do we add them? How do we simplify square roots with negative numbers inside? How do we multiply complex numbers so that we can use that skill set to solve a quadratic just like this one? So let's start by just working with negative numbers inside square roots and simplifying them. So if we have the square root of -1, we just said that that is defined, or that anytime we have a square root, we can take the negative out by sticking an I in front, and we know that the square root of -1, or the square root of 1, is 1. So I times 1 is going to give us I. So anytime we see a square root with a negative number inside, the very first thing that we can do is we can rewrite it with an I on the outside and then change the square root to be a positive number. So that I is telling us what kind of solutions we're going to have after we square root 25. Well, the square root of 25 is 5, so we can say that the square root of -25 is 5i. Now I want you to notice there's no plus or minus symbol here. The plus or minus symbol comes in when you have a function and you are the one that is square rooting both sides because you need to consider both solutions. In the case of all three of these examples, the square root is already here, so it's already telling you if we care about the positive or the negative version. Here, there's no negative in front of the square root, so we care about the positive square root of negative 25. We care about the positive square root of negative 72, and here we care about negative 5 times the square root of negative 9. So just keeping that in mind, the square root, the plus or minus, comes into play only when you square root both sides of an equation, and these are just expressions. So similarly with 72, with the square root of negative 72, I can take the negative away by putting an I in front, and then I'm going to simplify the square root of 72. And whether you're doing that, making a factor tree, also known as the upside down birthday cake, or you're using different properties to simplify, it doesn't really matter as long as you know how to simplify a radical. So I get to take 6 out, and the number I didn't use was 2. So the square root of negative 72 is equal to 6i times the square root of 2. And remember, to simplify 72, you could also say that 72 is the same thing as 36 times 2, and we know the square root of 36. Just don't forget your I. Okay, if we have a coefficient that's in front, that actually doesn't change anything. So I'm still going to take I out to make it positive 9. And then if I take the square root of positive 9, I get 3. And then I can just multiply to get that this is going to simplify to be negative 15i. Okay, now that we've worked with sort of the radical version of this, when we have a square root, let's actually look at what a complex number is and how it behaves so that we can focus on combining like terms and multiplying with complex numbers. A complex number can have both a real and an imaginary part. So it's a number of the form a plus bi, where a and b are real numbers. So it could be something like we just saw, where we have 2i, or it could be something like 3 plus 2i. We do want to write them in this form. The standard form for complex numbers is that the real piece, the part that is not imaginary, comes first, and the imaginary part comes second. So if we have an expression where we're comparing two complex numbers, we're going to compare the real part of the complex number to the real part of the other complex number. So on number 4 here, the real part is the part that's not connected to I. So if these two equations are going to be equal, that means that the two real components of the equations are going to be equal, which is going to give us that x must be 10. Then we can compare the imaginary pieces, negative 7i times y and y times I is going to mean that y would have to be negative 7. And if you need to, you could think of it as we're dividing both sides by I, and that's leaving us with y equals negative 7. So go ahead and pause the video and compare the real components to find x and the imaginary components to find y on number 5, and then unpause the video and see how you did. All right, hopefully you have had time to work through number 5. If not, go ahead and pause the video now. Here we're going to have that 5x is equal to 35, which means that x is going to be 7. Here we're going to have that negative 20i is equal to yi, so I can divide both sides by I and get that y is going to be equal to negative 20. So this idea kind of goes back to Algebra 1, where we were looking at things like 2 plus 2x, and we talked about how we can only combine things with the x term if they have an x, and we can only combine things with the constant term if they have a constant. Which means if we had more terms, like let's say x plus 9, we could combine the two things that don't have a variable, the two constants, and we could combine the two things that do have a variable, and we called that combining like terms. And this exact same process of combining like terms still works with imaginary numbers. When you combine like terms with imaginary numbers, you can combine the two pieces that are real. So in this case, 5 and 10. You can combine them to be 15, and then you can combine the two pieces that are imaginary, 4i and 8i, and if I combine those, I get 12i. But what I want you to notice, just like with this polynomial example below, is that 15 plus 12i, that's as far as we can go. We can't combine that to be 27i because 15 and 12i aren't like terms. One of them is an imaginary term and the other one is a real term. So keeping that idea in mind, we can treat imaginary numbers almost the same way we did polynomials when we're thinking about this in terms of operations. So let's look at a few more examples where we're adding and subtracting, and then we'll move on to multiplication. So here we have 3 examples where we're adding or subtracting with complex numbers. And we're going to see parentheses here, but one thing I want to remind you about is that addition, it doesn't matter what order we add in as long as we are adding like terms. And that just goes back to basic properties in Algebra 1. So even though I have parentheses here around 8 minus I and around 5 plus 4i, what I'm really doing is I'm just combining like terms. So I could regroup these. And I could say, well, 8 plus 5, those are the 2 real pieces, so I'm going to add them first. And then I'm going to add negative I and 4i. 8 plus 5 is going to give me 13. Negative I plus 4i is going to give me 3i. And I do want to make sure that after I'm done simplifying, which is all we're doing here, that I have the real piece plus or minus, depending on the situation, the imaginary piece. Now, if you look at number 7, we aren't adding. What's in parentheses is being subtracted. So we can't just drop the parentheses and combine like terms. We need to appropriately deal with this negative. This negative is really just saying, it's like there's a negative 1 here. We need to distribute that negative. So it's going to become minus 2i minus 7. Minus 2 minus 7i. And then the 13 isn't changing and this 5i isn't changing. Now that we've eliminated those parentheses, we can regroup things so that it's easier for us to compare the 2 real pieces, 13 and 2, or negative 2, that's going to give us 11, and the 2 imaginary pieces, negative 7i and 5i, and if I combine those, I'm going to get minus 2i. I'm going to encourage you to pause the video, decide whether or not you can just take those parentheses away or you need to do something first, and then combine like terms and write your final complex number in standard form. Okay, hopefully you have had time to do that. These parentheses are just being added, the first set to the second set, which means I can just regroup my 7 and my 3, my negative 6i and my negative 6i. This is going to give me 10 for my real piece, minus 12i for my complex piece or my imaginary piece. So this entire thing is called a complex number. It has a real component and it has an imaginary component. Now that we've looked at adding and subtracting complex numbers, let's see what happens when we multiply them. So at the beginning of this lesson, we talked about how I is the square root of negative 1, which means if we actually just applied some properties, right? If I is equal to the square root of negative 1, we could square both sides of this equation and we would end up with I squared equals negative 1. When we're multiplying, we're going to see I squared come up because just like when we multiplied with polynomials, if I multiply x times x, I get x to the second power. So if this was I and I was multiplying, I times I is going to give me I to the second power. The key thing is anytime you see I to the second power, that piece of your expression can be switched with or substituted in with negative 1. So when we're multiplying, this is going to be just like when we multiplied polynomials. You could multiply using the area model. That's something that people get comfortable with in Algebra 1, where you draw a box and you write one term across the top of the box and another term across the side of the box, and you multiply to fill in the box. That's a totally acceptable approach to take when you are multiplying, even with imaginary numbers. You can also just apply the distributive property, which is what I'm going to do here. So on number 9, we're just distributing. So I'm multiplying 4i times negative 6. That's going to give me negative 24i. And multiplying 4i by 2i, which is going to give me 8i to the second. Now, anytime you see I to the second, you're going to replace it, or you're going to substitute in negative 1 because I squared is negative 1, and we want our most simplified answer. So this is going to give me negative 8 minus 24i, and I'm going to specifically write it in that order so that the imaginary piece comes second. Now for number 10, we're going to have to apply the distributive method twice or use the box method, the area model that I discussed down here. If I multiply 9 times negative 4, I get negative 36. 9 times 7i, I get 63i. If I multiply negative 2i times 4, I get positive 8i. If I multiply negative 2i times 7i, I get minus 14i squared. So I have negative 36. I can combine these two imaginary pieces to get 71i. And then I'm going to swap or substitute in what I know I squared is. I squared is negative 1. So this term, when I multiply, is going to become positive 14. And I have negative 36 that I can combine with that. So negative 36 and positive 14 is going to be negative 22 plus 71i. Okay, I'm going to encourage you to pause the video and work through this last one on your own, and then unpause the video and see how you did. All right, step 1, we're distributing. That's going to give me 44 plus 32i. Then distribute my negative 12i, so that's going to give me negative 132i minus 96i squared. I can combine these two imaginary pieces. That's going to give me minus 100i. And 96 times I squared is negative 1, so this is going to become positive 96. 44 minus 100i plus 96, and then I can combine those like terms to get 140 minus 100i. So now that we've learned how to manipulate, how to multiply, how to add, how to work with the radical version involving imaginary numbers, we're going to extend this to the whole purpose of us learning about imaginary numbers right now where we're at, which is being able to solve a quadratic equation that has a complex solution. So let's go ahead and look at just 3 more examples that extend imaginary numbers to what we've been working with solving quadratics. Okay, so this first example looks like the one we actually already did at the beginning of this section. Right now, if you just take a quick glance, these problems don't look specifically different than what we've been doing already in chapter 3. So when I look at number 12, I'm asking myself, do I want to graph a function that would have these solutions? No. Can I factor it? No. That leaves me with the square root method. Is the only other one we've talked about so far. So I'm going to go ahead and isolate my squared term, which means I'm going to subtract 4 on both sides. Then I'm going to square root both sides, and now I see why this problem is showing up in this section, because I'm taking the square root of negative 4. So to get rid of the negative, I'm going to put plus or minus I in front, and the plus or minus is coming because I drew the square root on both sides. And the square root of 4 is 2, so this is going to be plus or minus 2i. You could also write this as negative 2i and positive 2i. I'm actually going to encourage you to pause the video and try and work through number 13 and 14 on your own, simplifying radicals, dealing with negatives inside by using your I, not forgetting your plus or minus, and then unpausing the video and see how you do. All right, hopefully you had time to work through this. If I add 11 to both sides, I'm going to get 2x squared equals negative 36. Divide by 2, so x squared is equal to negative 18. Take the square root of both sides, which is going to give me x squared equals plus or minus the square root of negative 18. And if we simplify this, we're going to get plus or minus 3i times the square root of 2. For me, I'm thinking the square root of 18 is the square root of 9 times 2. That's where the 3 is coming from. Or you can make your upside down birthday cake. And then last but not least, number 14, I'm going to subtract 20 on both sides. I'm going to divide by 4. And then I'm going to square root. X is going to equal plus or minus I root 5. And then 5 is prime. It doesn't simplify at all. So this is going to be my final answer here. So key ideas in this section. Complex numbers allow us to solve quadratics like the quadratics that we just solved that have a negative inside the radical. And we need to not try and think about what that would look like visually on the graph, other than the fact that if we have imaginary numbers, it means the graph of our quadratic isn't crossing the x-axis. But we want to use those so that we can come up with solutions that involve complex numbers. We also focused on how to deal with that negative inside the radical by taking I out, and we focused on adding, subtracting, and multiplying with imaginary numbers and what those properties are. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.